atomic mass. This is the mass that is listed on the periodic table for each element, and when you look at these masses, they go out several decimal places. So the atomic mass, it is a weighted average. So it's a weighted average mass of an element's naturally occurring isotopes. The atomic mass is simply a summation of each isotope's mass number multiplied by its percent abundance. So the atomic mass, the mathematical equation, this is not in your reference tables. This is something you need to get memorized. But I always suggest, highly suggest, that you write this on the back of table T so that you see it and remind yourself how to calculate an average, a weighted average mass. So it'll be the isotope's mass number times its percent abundance plus the second isotope's mass number times its percent abundance, and you keep this going until all isotopes and their percent abundances are represented. So let's look at an example here. Or the next thing I want to remind you is that the percent abundances, so the percent abundances, when you take this percent abundance and you add it to this percent abundance and add it to this percent abundance, the individual percent abundances, they should sum to equal 100% at the end of the math. So let's look at an example here. Let me move my page up. So we are working with the element boron, and it's stated that it has 2 naturally occurring isotopes, so we need 2 sets of the parentheses. So we have our first isotope, its mass times its percent abundance. So I'm going to write isotope 1 plus the information for isotope 2. So when I take a look at this, the first isotope is boron 10, and I'm not told anything else about it in reference to mass, so that hyphen number is what we will use for the mass number. So isotope 1, it's 10 AMUs times its percent abundance, which is the 19.9%. So I have mass times the percent abundance. When I look at the second piece of information, we have boron 11, and we are only told it's boron 11, so we'll use the hyphen number 11 as its mass number. So the second isotope's number of AMUs is 11 AMUs, and then it says it makes up the remainder of the element's abundance. So to get this piece of information, I would quickly calculate 100 minus 19.9. So boron 11 makes up around 80.1% of all boron atoms. So now I need to divide out this by 100% to eliminate or reduce out the percent signs, so that mathematically I am just left with the AMUs. Record your average atomic masses that you calculate out to the nearest hundreds. So when I put this in the calculator, it becomes 10.80 AMUs. Now, does this answer make sense? Because it's a weighted average, whatever you calculate for the atomic mass of an element, it must fall within the range of the given isotope masses. So 10.80, this falls between the isotope mass of 10 and 11, so it makes sense. Okay, so let's take a look at another example here. Okay, so now this time we are told that this element silicon, so silicon has 3 naturally occurring isotopes. So since it has 3, we need 3 of those parentheses setups. So isotope 1 plus isotope 2's information plus isotope 3's information. So my first isotope is said to be silicon 28, and because I'm not told anything else, I will use the 28 as its mass number. So 28 AMUs times its percent abundance of 92.23%. My next isotope is identified as Si29. I'm not told anything else in reference to mass, so I'm going to use the 29 AMUs. So 29 AMUs times a percent abundance of 4.67%. And then I have my third isotope, silicon 30, Si30. So I'm going to use the hyphen number as my mass, 30 AMUs times its percent abundance of 3.10%. So I put that all into my calculator, just like I've written it out. And then I need to divide that answer by 100%. And when I take a look on the calculator, the weighted average AMU is 28.11 AMUs. And when I compare my calculated answer to the elements' mass numbers that are provided, this falls. It's greater than the lowest mass number, and it's less than the highest one. So this average atomic mass makes sense. So now, can you make a correlation between the average mass that you see on the periodic table and the isotopic information? So let's take a look at boron. So boron has 2 known isotopes. So this is the mass number, and up here I'm going to put the percent. So boron was given 2 different mass numbers, a mass of 10 and a mass of 11. And when you calculated the average atomic mass, it was 10.8. So the 10.8 would be here, like on the number line. So that's my atomic mass. And so does this make sense? The isotope with a mass of 10, its percent abundance was around 20, and the isotope with a mass of 11 made up around 80% of the abundance. So the average atomic mass value is closer to the isotope's mass number with the larger percent abundance. We can do something similar for the silicon. So the Si, we were given 3 different isotope masses, a mass of 28, a mass of 29, and a mass of 30. The weighted average came out to be 28.11, so that would be about right here. So that's our atomic mass. And does that weighted average make sense based on the percent abundances? Well, the isotope with a mass of 28 makes up around 92% of all Si atoms. The 29 makes up around 5%, and the Si atoms with a mass of 30 make up around 3%. So Si28 has the greatest abundance, so its atomic mass would be closest to it. So write yourself a note that the average atomic mass value will always be closest to the isotope with the greatest percent abundance. So you can predict which isotope is probably the one with the largest percent, something like carbon. So carbon has two isotopes, carbon 12 versus carbon 14, and the PT mass is 12.01 with several decimal places. So what is the more common isotope of carbon? Well, it's carbon 12 because the average weighted average mass is much closer to a mass number of 12 than 14. So carbon 12 is the more common isotope.